All right, the last piece of stoichiometry we're going to look at in this unit is limiting and excess reagents. So, way long ago, we made some s'mores, and you did this s'mores stoichiometry worksheet. So, if you had 40 grams of chocolate, 5 grams of marshmallows, and 80 grams of graham crackers, how many s'mores could you make? Well, we don't really know. We have to know how to turn the mass into the number of pieces. So we need the mass per piece before we can go ahead with this. So this is kind of like chemistry, where you need to turn grams into pieces, aka moles, before you can understand how many of something you can make. So if we were going with 2 graham crackers, 1 marshmallow, 1 piece of chocolate makes 1 s'more, how many s'mores could we make if we have 10 graham crackers, 6 marshmallows, and 7 pieces of chocolate? Well, with 10 graham crackers, technically I could make 5 s'mores. With 6 marshmallows, I could make 6 s'mores. And with 7 pieces of chocolate, I could make 7 s'mores. So overall, I can make 5 s'mores. So what limits the number of s'mores produced? It was our graham crackers. This is called the limiting reagent. What reactants were left over? Marshmallows and chocolate. These were called our excess reagents. So our goal here is to identify and predict theoretical yields for limiting and excess reagents. Theoretical meaning stoic. All right, a few assumptions again. All reactions are spontaneous. All reactions are fast. There's nothing to indicate how quickly a reaction is going to go. You actually just have to wait it out. But reactions are quantitative, meaning they are more than 99% complete, aka it goes to completion. We don't have A plus B making C, D, and it just stops halfway without any warning. Reactions are stoichiometric, meaning chemicals react in simple whole number ratio, and that's the coefficients of our balanced chemical equation here. Okay, the quantity of product that results from a chemical reaction is limited by the reactant that is used up or completely consumed first. So the limiting reactant or reagent, those two words are interchangeable, is the reactant that is completely consumed in the reaction. The limiting reagent determines the maximum quantity of product or products that can arise from a chemical reaction, kind of like our marshmallows, graham crackers, and chocolate. The graham cracker was completely consumed, and it determined the maximum quantity of products or s'mores we could make. Note, it does not need to be the reactant present in the fewer number of moles or fewer pieces, and it is not necessarily the lowest mass reactant. So in our previous example, we had 10 graham crackers, which wasn't the lowest number, yet it was the limiting reagent. So don't take the number of pieces or the number of moles of just one compound. We have to think about how many products it can make before we can decide if it is limiting or excess. The excess reactant or reagent is the one that it remains after the reaction has taken place, is kind of the leftovers. How do you identify a limiting reagent question? Well, first of all, it's stoichiometry. You're given information about one thing and asked about another. However, in the limiting and excess question, you will actually be given enough information to determine the amount of both reactants, or at least 2. Only one of the reactants will be the limiting reagent. So we have to figure out who is limiting before we can continue on with our question. Steps for solving these questions: write the balanced chemical equation, organize your information, find the number of moles of both reactants, switch the number of moles of both reactants to one product. Okay, so we're going to pick one thing and we're going to turn them all into product representing that one. And then calculate the desired answer using the given information for the limiting reagent only. Okay, again, that's the smallest number of moles of product produced. So these are really the similar steps. It's just that we're doing it twice to calculate the moles of reactant and switch moles. Best way to do this is to practice. So which reactant would be limiting if 4 grams of chromium and 200 milliliters of 0.125 moles per liter iron 2 nitrate were reacted? First step, chemical reaction. So chromium is a solid element, and iron 2 nitrate is in solution, again, because it has a concentration here. So we're going to create chromium nitrate, and it's chromium 3 because that's the most common charge for chromium. And we're going to create iron as a solid. To balance, we need 2 chromiums, 3 iron, 3 nitrates. We're going to make 2 of these, and we need 3 irons. So we haven't been asked, we should write out our information first before we get going here. Okay, we had a mass of 4 grams. Our molar mass of chromium, again, we do not consider the 2 when we are determining molar mass. Just 1 chromium is 52. We have a volume of iron 2 nitrate, and we have its concentration. So technically I can find moles of both of these. That's how I know that this is limiting and excess, plus which reactant would be limiting is the giveaway. So in this case, we aren't asked to decide how much product is produced. We just need to pick a product that we're going to turn moles of each compound into. So I'm going to pick iron. So I'm going to switch both of these to iron. I'm going to see how much iron they could produce, and I'm going to choose the smaller number to be my limiting reagent. If this was a question where it was asking how much precipitate was produced, that would be the clear deciding factor on who to convert to. Okay, so because we're going to do this twice, stay organized. So we're going to start with chromium. We're going to use N is equal to little m over big M, and we're going to find the number of moles of chromium represented by 4 grams. So divided by 52. If you plug that into your calculator, you get 0.07692 moles, and that's moles of chromium. Now, we need to convert that into product before we can compare it. It's like deciding how many s'mores we can make before we decide who's our limiting reactant there. So moles of chromium are on the bottom, and again, I'm going to convert to moles of iron. You could have chose chromium 3 nitrate, doesn't matter. You'll get the same answer for who is limiting and who is excess. So there's 3 moles of iron produced for every 2 moles of chromium reacted, and we get 0.1154 moles of iron or product. Now we're going to do the exact same thing, but we're going to do that with iron 2 nitrate. So this time we're using C equals N over V to find moles. So N is equal to C times V, which is equal to 0.125 moles per liter times 0.200 liters. And this gives us 0.025 moles, and that's of iron 2 nitrate. So we still need to multiply by our mole ratio, so times, we need to cancel moles of iron nitrate, and we're looking for moles of just iron. So this is a 3 over 3. We're going to get the exact same number of moles. Moles of iron. Okay, it's at this point that we can decide who is limiting and who is excess. So the smaller number of moles of product produced is here, 0.025. That is less than our 0.1154. This came from our calculation using iron 2 nitrate. Therefore, iron 2 nitrate is the limiting reagent. So again, what this says is we have 4 grams of chromium, which is equal to 0.07692 moles of chromium. This produces, if all 4 grams reacted, we would get 0.11 moles of product. With iron 2 nitrate, we had 0.025 moles of iron 2 nitrate. It is able to produce 0.025 moles of iron nitrate if it was able to react to completion. We know that this will react to completion. This will run out of its companion, iron 2 nitrate, before it can make this much product. All right, you are supplied with 9 grams of sodium iodide and 6.5 grams of lead nitrate, and you dissolve each in a beaker before mixing the solutions. What is the mass of precipitate formed? So I'm going to do this one using unit analysis and show you how we would do that with limiting and excess. First step, always write a balanced chemical equation. So you're going to get sodium iodide, which is dissolved before reacting, and lead 2 nitrate, which is also dissolved before reacting. So both are aqueous. We're going to make PbI2, which is a precipitate, and NaNO3, which is aqueous. To balance, we need 2 of these. We're going to make 2 of those. Write out the information we have. And we are looking for the mass of precipitate formed. So the mass of this is what we're looking for. Find our molar masses. 149.89 grams per mole here. Molar mass is 331.22 grams per mole. And over here, the molar mass is 461.00 grams per mole. Okay, so unit analysis. We're going to stay organized still, so write out who you're calculating the moles of. And we're going to start with the mass. So 9.00 grams. And we need to cancel grams and find moles of NaI. This is our molar mass, so 149.89 grams per 1 mole. Grams cancel. Then we need to convert to moles of product. So we're looking for moles of PbI2, and we need to cancel moles of NaI. This is a 1/2 ratio. Moles of NaI cancel. Now you have 2 options here. You can go right ahead and calculate the mass of product formed, or you could stop at moles, compare with our next one, decide who is limiting in excess, and finish the question. I'm going to show that we can just go right to mass. So moles of PbI2 cancel, and we're finding grams. This is our molar mass, so 461 grams per 1 mole. Moles cancel. When I calculate this out, I get 13.8 grams of PbI2 produced if all 9 grams of NaI react. So let's go ahead and we're going to do the exact same thing for lead 2 nitrate. So we're going to start with it 6.50 grams, and we're going to cancel grams and find moles. And that is 331.22 grams per 1 mole. Our mole ratio is here, so moles of PbNO3 are canceled on the bottom, and we are finding moles of PbI2 up top. This is a 1/1. We still show it. We're at moles, we're going to find mass. So this is 461 grams per 1 mole of PbI2. When we calculate this all out, I get 9.05 grams of PbI2 produced. So we always choose the lower mass. If all 6.5 grams of lead nitrate react, we get 9.05 grams of product. If all 9 grams of NaI were allowed to react, we got 13.8 grams of product. We will never get 13.8 because I'm going to run out of lead nitrate first. So who was limiting? PbNO3 was limiting, and 9.05 grams of PbI2 was produced. All right, this is a big example and it combines a lot of ideas. The first step here is we're going to decide who is limiting and who is excess in each beaker or flask, sorry. So I combined solutions of copper 2 nitrate and sodium hydroxide in 2 different sets of concentrations in labeled Erlenmeyer flasks 1 and Erlenmeyer flask 2. So we're going to determine the limiting and excess reagent in each flask. Now this is the same reaction in both, so I'm just going to write out one general reaction for us. So copper 2 nitrate, solutions of that and sodium hydroxide are combined. And we're going to make sodium nitrate solution. And we get a copper 2 hydroxide precipitate. To balance, we need 2 sodium hydroxides, and we're going to make 2 sodium nitrates. All right, in flask 1, we had a volume of 50.0 mils and a concentration of 0.3150 moles per liter for sodium hydroxide. And we used 50 mils of copper nitrate, and our concentration is 0.08972 moles per liter. So typically we use a precipitate is what we're going to be finding. So I'm going to use this one as who I'm converting everybody into. So let's start with copper to nitrate. I'm going to use unit analysis. Because I don't need a mass, I just need to determine who's limiting and who's excess. I'm going to stop at moles of product. So 0.05000 liters times 0.08972 moles per 1 liter. And our mole ratio from copper nitrate to copper hydroxide is 1 mole per 1 mole. So we get 0.004486 moles. We're going to do the exact same thing for sodium hydroxide. I'm just going to pause the video and do it. Okay, we can see that we get 0.007875 moles of product when all the moles in our 50 liters of 0.3150 moles per liter solution of NaOH react. So in flask 1, we can find that copper nitrate was our limiting reagent. So NaOH was in excess. We're going to go ahead and do the exact same thing for solution 2, or sorry, Erlenmeyer flask 2. So we had 50 milliliters of our copper nitrate, and it had a concentration of 0.3029 moles per liter. Our volume of sodium hydroxide and our concentration of sodium hydroxide didn't change in this case. So if this didn't change, it's the exact same thing as above. So NaOH can make 0.007875 moles of CuOH2. Again, I'm just using the information here because it was exactly the same. So we need to calculate copper nitrate again though, because it is slightly different. So 0.05000 liters times 0.3029 moles per 1 liter. Our mole ratio hasn't changed. And in this case, we get 0.01514 moles of copper hydroxide. So in flask 2, we can see that limiting and excess has swapped. So in flask 2, copper nitrate is excess and sodium hydroxide is limiting. So they've swapped between the two experiments here. Now part B asks us to qualitatively describe the filtrate solution in each flask. So what this is asking is, in general, what are you seeing? So the properties of the solution, is it acidic or basic? Does it have a solution color? Those are the things we're looking at. And the filtrate is, remember, we've poured 2 solutions together in this flask and we've created a precipitate at the bottom. Then the filtrate is the solution. So the filtrate is the aqueous solution up top, and it does not contain the precipitate. The bottom, again, is the precipitate, and it's the solid. Okay, so flask 1, what we had is I had 2 beakers of solution, remember. I had a beaker of solution of NaOH, and I had a beaker of solution of copper nitrate. Together we mixed them, and we made one solution with a precipitate in the bottom of the flask. So the precipitate, again, was copper hydroxide. And then in the flask, we need to decide what is in this solution. So NaOH in our first experiment was in excess. Copper nitrate was limiting, meaning there was fewer molecules of those, and it's the one that gets used up completely. So what I drew in mine is that I have 1 copper with a nitrate. So it's like I have 1 of those. Okay, and because it's aqueous, it's dissociated into its ions. Water isn't a big piece of this, so we're not looking at it. Now, NaOH is in excess, so I'm going to have lots of those. So I'm going to have maybe 3 NAs, and that means there's going to be 3 OHs. Now, 1 copper binds with 2 OHs. So from our previous flasks, this copper has been taken care of here, and we're going to cross out 2 OHs. Now everything else that's left in this flask, these flasks, gets added to our filtrate solution. So these are still dissolved ions in solution. So I have 2 nitrates, I've got 3 sodiums, and I've got an OH minus. There's no copper ion floating around in solution because I've used it all up and it's in my precipitate here. Okay, what do we know about these solutions? NaOH is basic because there's an OH minus ion present. Copper nitrate is blue. It's a blue solution because of the copper 2 plus nitrate. It's copper 2 plus, ion that's free and floating around. So what do we see in our precipitate? Well, I see an OH minus ion floating around, meaning that this will be a basic solution. So there's OH minus left over. Are there any Cu2 pluses though? No. The Cu2 pluses that are here are stuck within this precipitate. So the solution, what's in solution, none of these ions have colors. Therefore, this solution is colorless. So there's no Cu2 plus ions free in solution. Okay, that's flask 1. Let's take a look at flask 2. Very similar idea. So we're going to draw our 2 solutions that we have in beakers. We add them together and we make the same precipitate, CuOH2, in the bottom of our Erlenmeyer flask. And we're going to decide what ions are still floating around. So we had NaOH, and this time it was our limiting reagent. So we're going to have a very few of these. I'm going to say that we'll have 2. All right, now copper nitrate is in net excess. So I'm going to draw, 2 of them because remember they have different coefficients, so this should work. Okay, now I have copper hydroxide in my precipitate here. So I'm going to cross out a copper for every 2 hydroxides. Now I'm out of hydroxide, so that's all the copper hydroxide I could make, and everything else is listed as ions in my solution here. So I have a copper 2 plus ion, I've got 2 NAs, and I've got some nitrate ions. Doesn't matter how many there are, it just matters if they're there or not. So in this solution, I still have copper 2+, and copper 2+ in solution is blue. So this solution will have a blue color because Cu2+ is a free ion. Now, there are no OH- ions, nor are there any H+ ions. Remember, H+ make them the solution acidic, OH- make it basic. So this solution is neutral. There are no free OH- ions. So this is a way of representing it in pictures. Some people will prefer, though, if you looked at the net ionic equation for this overall, you would find that you get Cu2+ and 2 OHs making CuOH2. Whatever this came from, so this came from copper nitrate, and this came from NaOH. If we knew that in this case, let's look at flask 1 again, NaOH was in excess. I'm going to use up all of the copper 2+. I'm going to have some leftover OH-. Therefore, I know that it's going to be basic because I have some of these left. I have no more copper 2+ ions left in solution if this is the limiting reagent. Therefore, it will be clear or colorless. So you can look at it using our net ionic equation too, rather than having to draw it out. But you do have to reason what's going on here. All right, you've got some practice to do. The last example was above and beyond anything you're going to find in your practice. So make sure you understand it, but know that it's really like that top-notch question. It's what you'll need to answer to get 100% across the board in a Chem 20 situation. Again, because we're just trying to make sure you understand the content being presented using our assessments, you probably won't see something to that level, but thinking about those physical properties as you're going through these questions is something to consider.